Welcome to This Explainer. Today, we're diving straight into the invisible architecture of your day. You know, every single time you tap a screen, search for a name, or hit undo, there's a brilliant hidden system pulling the strings in milliseconds. We're going to explore exactly how these systems operate, starting right at the bedrock of it all. So think about this. How does your phone instantly render every single pixel on your screen? Well, it all comes down to the absolute foundation of everyday computing, and really, seeing how array storage works daily. At a low level, your machine just needs to store data in memory in a very precise, ordered way. And that brings us to the array. It's essentially a fixed-sized, ordered collection of items where every element sits at a numbered position. Think of it exactly like seats in a movie theater. Because every single seat has a precise label, seat 1, seat 2, and so on, your computer can instantly jump directly to seat 47. It completely skips checking the first 46. Every item lives right next door to the other, so the computer never has to guess where things are. But let's be real. Here lies the array's fatal flaw. Reading from an array is blazing fast, operating at what we call O of 1 speed. But modifying an array, that is painfully slow, because it requires shifting thousands of items just to make space. Since its size is locked in when it's created, squeezing a new piece of data right into the middle means you literally have to bump every subsequent element down a spot. It's a massive bottleneck. And that leads us to the evolutionary response, breaking the array's rules for flexibility. The crucial takeaway here is that pretty much every other data structure we're looking at today evolved specifically to solve the problems that this rigid array just cannot handle. Enter the linked list. So while our daily array forces everyone to sit together in a neat little row for fast reads, a linked list scatters the seats around, trading that instant read speed for incredibly fast changes. It's basically a treasure hunt. Each clue only points to the next clue. Because the items don't have to sit next to each other in memory, squeezing a new clue into the middle just means updating 2 pointers. Bam! Instant insertion, whether you're dealing with 10 items or 10 million. Now, what if we take these linear structures and heavily restrict them? We get highly specialized linear structures. A stack is last in, first out. Just like stacking plates in a cafeteria, you only touch the top plate. This is exactly what powers your Control+C undo feature or your browser's back button. Then there's the queue, which is first in, first out, like waiting in line at a coffee shop or sending jobs to a shared office printer. And the deck? It's double-ended. It lets you add or remove from both the front and the back, making it absolutely perfect for sliding windows or jumping forward and backward in your browser history. But what happens when your data scales up? What if you want to instantly find a specific contact without scanning the whole list? This is where flat lists and arrays really start to choke. If you have millions of items and you just want to find mom in your contacts, you definitely don't want your phone scanning every single name from A to M to find her. So let's look at the hash map retrieval process. Understanding this step-by-step is a total game changer. First, you provide a key, like mom. Next, it runs through a mathematical formula called a hash function. Third, it converts that word directly into a memory slot, let's say 4,827. Finally, it jumps directly to slot 4,827. Boom. The size of your contact list completely stops mattering, because finding that one item is always instantaneous. Now, what if we don't even care about the phone number attached to the name? That's where we use a hash set. It's a hash map with no values, just keys, functioning exactly like a nightclub bouncer checking a guest list. The bouncer doesn't care what table you're sitting at. They just need to know, are you on the list, yes or no? A hash set gives you that instant yes or no, completely bypassing the slow linear search of an array. Okay, so far we've been living in a 2D world, but moving from flat lists to branching hierarchies changes everything. Real-world data branches outward, kind of like your computer's file explorer. And for that, you need a tree. Let's look at the binary search tree. It operates exactly like a number guessing game. Say we're guessing between 1 and 1,000. You guess 500, I say too high. You just eliminated 501 to 1,000. Next, you guess 250, I say too low, you eliminate 1 to 249. Because the left side of the tree is always smaller than the right, every single step down eliminates half of your remaining data. It literally turns a million agonizing checks into just 20 simple steps. But hey, sometimes you don't actually care about searching through a massive sorted list. A binary search tree is great for finding sorted data fast, but what if you need instant access to the highest priority item right this second? For that, you need a heap.
As the saying goes, urgency beats arrival time. The most critical case always jumps to the front automatically. Think of a heap exactly like an emergency room triage. If a heart attack rolls in after a minor headache, the data structure automatically reorganizes itself. The critical case is always sitting right at the very top. It doesn't bother sorting the whole waiting room. It just ensures the absolute highest priority item is immediately accessible.
And then there's the try. This is a prefix tree, where each level represents one character, narrowing down possibilities with every keystroke. It's the silent hero powering your daily autocomplete. The second you type A, then P, you've already branched past millions of useless words to land right on a branch containing Apple or App Store.
All right, let's step away from neat, organized hierarchies. We need to talk about complex webs for when data is just messy and chaotic. Because sometimes data connects in every possible direction.
Enter the graph. A graph is a network of dots, which we call nodes, and lines, which we call edges, used to map out those messy, chaotic relationships. Whether it's mapping the edges of Facebook friendships or calculating the shortest road connecting to cities in Google Maps, graphs are the massive webs connecting our world. Now, to navigate specific groups within those massive webs, we use a disjoint set, or union find. Look at these real-world uses. Figuring out who knows who indirectly at a 100-person party, checking if two computers share network, or finding out if pixels form the same object in image processing. It tracks connected groups, and get this, it actually compresses its own paths so it runs faster every single time you use it.
Okay, prepare yourself for the weirdest rule breaker in computer science. A data structure that's super fast, uses almost no memory, but occasionally lies to you.
Meet the Bloom filter. The results are fascinating. If it gives you a no, that is 100% guaranteed truth. But if it says yes, it's mostly true, but it might be a false positive lie. So why use a structure that lies? Space and speed. By accepting a tiny risk of a false positive, a Bloom filter can instantly check if your password was leaked in a massive database, saving gigabytes of memory by only storing mathematical hashes instead of actual text. Finally, we have to talk about pure survival. When your computer runs out of memory, how does it decide what to instantly forget? It actually marries two concepts we've already covered to solve this. It's called the LRU cache, or least recently used. It's a brutal, highly efficient combination of a hash map and a doubly linked list that evicts the oldest data first. The hash map gives you those instant lookups, while the linked list pushes recently used items right to the front and silently chops the forgotten data off the back. It keeps your CPU and browsers blazing fast by just letting go of what you haven't touched in a while. So from how array storage works daily to power the pixels on your screen, right down to the Bloom filter lying to protect your passwords, which invisible structure is silently organizing your next click? Every tap, swipe, and search relies on these brilliant evolutionary trade-offs. What else in your digital life is hiding a brilliant compromise? Keep wondering, and I'll see you in the next explainer.